Hi students, welcome back to this tutorial. In this video, we can learn how to convert a decimal number into its binary equivalent form. And also, we can check whether the generated binary equivalent is exactly equal to the decimal value or how much it is accurate. Okay, so consider one example. Here we have a number 120 which is in decimal form, and our task is to convert this into its binary equivalent form. Okay, so for performing this, what we want to do, we want to perform the division. Divide this 120 using this binary base value 2. Okay, so follow these steps. First, divide this 120 using this 2. So, while performing this division, we get a quotient 60 and the remainder 0. Right? So, divide again this quotient value using the same base value 2. So, while dividing this 60 with 2 again, we get a quotient 30 and the remainder 0. So repeat it again. That means divide 30 with the base 2. Now we get the quotient as 15 and the remainder as 0. Again, divide this 50 by the base 2. Now get the quotient as 7 and remainder as 1. Repeat again. Now 7 divided by 2, it is quotient is 3 and remainder is 1. Divide again this 3 by 2. Now we get quotient as 1, remainder as 1. Now here the quotient is 1 which is less than this base 2 or the divisor which is less than, quotient is less than our divisor. So now we can stop here. And the next step, arrange these zeros and ones in this particular order. Start from this and move in this direction. So the binary equivalent of decimal 120 is 111100. Okay, so this is the method for converting a decimal number into its binary equivalent. Divide the given number using the base 2 again and again until we get a quotient which is less than our base 2. Then arrange this remainders in this particular order. So this one is our binary equivalent of decimal 120. Now check whether this binary value is equal to this decimal 120 or not. How to perform this? For that, we want to perform or we need to find the place values. Then we want to multiply the place value with the corresponding digit or corresponding bits. This particular method of conversion from binary to decimal is already discussed in our previous video. Okay, so consider this particular number. Next step, find out the positional values. This 0, 2 raised to 0 and 2 raised to 1, 2 raised to 2 like this. Now perform the multiplication and addition. That means 1 into 2 raised to 6 plus 1 into 2 raised to 5 plus 1 into 2 raised to 4 plus 1 into 2 raised to 3. And these three terms. Here the bits are 0. So multiplication returns a result, a product value equal to 0. So no need to multiply this. Okay, so while adding these values together, 64 plus 32 plus 16 plus 8, it is 120 in decimal. Exactly equal to the decimal number. Okay, now we can consider one more example. But here the given number and the decimal form is a fractional number and which is 0.25. And our task is to convert this 0.25, this fractional number 0.25 into its binary equivalent. So in this particular case, what is our procedure? we want to multiply this 0.25 using our base 2. In case of fraction, we want to perform multiplication. In case of a whole number, we want to divide continuously using the base value 2. But here, in case of fractional number, we want to multiply the fractional part using base 2. So while multiplying this, we get a value 0.50. Okay, so keep this whole part as such it is and consider or focus here in this fractional part only. Okay, so take this fractional part only and multiply again using the base value 2. Now we get 1.00. Here the fractional part becomes 0. That means the further multiplication always returns value 0. So now we can stop here. Why? Because the fractional part here it is 0. So the further multiplication returns 0 again. So now we can stop here and consider the whole part of these partial products only. We need to consider the whole part only, but the direction is from top to down. Okay, so the equivalent of this 0.25 is 0.01. 01. Okay, so 0.25 in decimal is equivalent to 0.01 in binary. Now we can check whether it is correct or not. Okay, so 0.01 is given in binary. Now we want to find out the decimal equivalent of it is. For that, we want to find out the place value and we want to multiply, then add values. Okay, so this 0 present just after the decimal. Okay, so here it is 0 into 2 raised to minus 1 plus this 1 into 2 raised to minus 2. So while adding this value, this one is 0 plus 1 into 2 raised to minus 2 means 1 by 2 raised to 2, that is 1 by 4. So this is 0.25 exactly. Okay, now we can consider one more example. Here it is 13.15 in decimal and our task is to find its binary equivalent. So in this case, what we want to do, we want to find this whole parts binary equivalent separately, then the fractional parts binary equivalent separately. Okay, so first focus on this whole part, that is 13. For converting a whole number into its binary equivalent, what we want to do, we want to perform division, a sequence of division by 2. Right, so first perform 13 divided by 2. While performing the division, we get a quotient of 6 and the remainder 1. Again divided this 6 by 2. Now get quotient 3 and remainder 0. Again divide this 3 by 2. Then get a quotient 1 and the remainder 1. Now the quotient become less than our base value 2. So now we can stop here. Then arrange these zeros and ones in this particular order. Okay, so the binary equivalent of this 13 is 1101. Right. Next, we want to find the fractional parts binary equivalent. In order to get the binary equivalent of a fractional number, what we want to do, we want to multiply it again and again using the base value 2. Right. So first 0.15 into 2. It returns 0.30. Now keep this whole part there and focus on the fractional part. Multiply again this 0.30 using 2. Get 0.60. Keep this whole part there and consider the fraction. 0.60 multiplied by 2 gives 1.20. Okay, so repeat this again and again. Next, 0.20 multiplied by 2 gives 0.40. Again, 40 multiplied by 2 gives 0.80. Okay, here we want to repeat this again and again because still now we didn't reach a point where the fractional part equal to 0. So we want to repeat it again and again. So continue. 0.80 into 2, this is 1.60. So again, repeat this. 0.60 into 2 gives 1.20. So look at this product values. Here this 1.20 is already generated here in this particular step. That means after this particular multiplication, it will generate the same sequence of these partial products, right? This 1.20, in next step it generates 0.40, and in next step it generates 0.80, and in next step it is 1.60, and in the next step it is 1.20, and repeat it again, right? So if we want, we can stop here and find the binary equivalent of this 0.15 as the whole part in this particular direction. That is 0.001011. Okay, if we want more accurate result, we need to continue this step and generate more and more number of product terms. Okay, so in this case, consider the procedure of converting this binary equivalent back into its decimal and check how much accurate this result. Okay, so for that, consider this this binary equivalent value, and using the place values, we can generate here the binary equivalent. Here it is. This 0 comes just after the decimal point. So 0 into 2 to the power minus 1, 0 into this 0 into 2 to the power minus 2, and next 1 into 2 to the power minus 3. That is 1 into 1 by 2 to the power 3. 1 by 2 to the power 3 means 1 by 8. 1 into 1 by 8 plus next two terms are 0. This is present at 2 to the power minus 4, 2 to the power minus 5, and this one is at 2 to the power minus 6. So that is why 1 into 1 by 2 to the power 6, that is 1 by 64, plus 1 into 1 by 2 to the power 7, that is 1 by 128. So while adding all these result together, we get a value 0.1484, which is nearly equal to our decimal value 0.15. Okay, if we stop here and consider these whole parts as the binary equivalent, it will generate a fractional number or a decimal equivalent which is exactly equal to this 0.1484, which is nearly equal to our 0.15, right? So again consider the same, and now I'm going to take more and more number of terms. 0.15 into 2 is 0.30, 0.30 into 2, 0.60, 0.60 into 2, 1.20, and again this 0.20 into 2, 0.40, this 0.40 into 2, 0.80, 0.80 into 2, 1.60, 0.60 into 2, 1.20. So here I'm not going to stop here. I want to generate more terms. Okay, so again 0.20 into 2, 0.40, 0.40 into 2, 0.80, 0.80 into 2, 1.60. Okay, now I am going to stop, and the fractional parts binary equivalent is taken as 0, 0. Sorry, consider one more term, and the fractional part binary equivalent is taken as 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1. Okay, now consider its decimal equivalent. That is this 1 into 2 to the power minus 3, that is 1 by 8. plus 1 by 64 plus 1 by 128 plus, and this one present at 2 to the power minus 10. That is why 1 by 1024 plus, and this is 1 by 2048. So, by adding these values together, we get 0.1499, which is more accurate, or which is more nearer to this value 0.15. Okay, from these examples, it is clear that while converting a fractional number in its decimal form into its binary equivalent, of the cases like this, that means while performing this multiplication, and at some point the fractional part of this multiplication become equal to 0, then no doubt we can stop right there and arrange this all part in this direction. That means from top to bottom. Then generate the exact binary equivalent of this decimal fractional number. Okay, and of the cases like this, that means while performing this multiplication, here it is clear that in this product terms, it never converging towards 0. And also the patterns are repeating. So in this case, if we consider more and more terms or more and more bits in our binary equivalent, in that case, the generated binary equivalent become more accurate result. Okay, if we consider more and more terms, it will become more accurate binary equivalent of our given decimal number. Okay, so all these are about converting a decimal number into its binary. Okay, so in our next video, we can consider the similar conversion of a decimal number to its octal form. Okay, thanks for watching.